Let's start recording. Hopefully it works. Hopefully there isn't a big problem. Oh shit. Might be actually what's going on here. Stay co-host. Okay, we're good. All right. So finally off our geometric high horse. No, sorry, algebraic high horse and going to geometry. And the first thing we're bound to have is, of course, the classic definition again. And the first thing we're gonna say is a lot of things you're gonna already know. Array. I need to talk what array was. Honestly, it was bound to happen. It's not something that I wouldn't happen. Segment, a line, and a right angle. Yeah. So although I do not like some of these uh definitions due to me never using it like this, I see the value in it, but I mean, in Khan Academy, the worst thing about it, the geometric section, was me doing match on this stuff because it was so obvious to me. I just didn't understand why you need like 15 practice problems on this. In my opinion, you do not need that much. Um, so all I remember is all the pain in Khan Academy, like doing 16 questions on this stuff. I was like, why the freak am I doing this stuff? All right. So all you need to know is that this is an array. So you just need to end one x segment and one direction vector. That's it. And this is array, but it should be called a vector. And in my opinion, a vector is the superior option to say what this is because oh wait. I just forgot. I don't think I ever explained some of these absolute value stuff. Oh. Okay, we're going back to here actually because I don't know if I actually did this. Did we? No, I think we left off as polynomial actually. I'm forgetting where I end off. Oh no, I'm gonna have to do a lot of stuff. Okay, screw geometry. We're not done yet with this stuff. Okay, so we're starting off. I'm gonna change the color of this because I'm not happy. I mean, I'm fine with the. I think. Oh, no, I don't like that either. You know what? Classic black is always the best. Um, so if you're given x minus one, all you have to do is just do the I forgot commutative or disputed property, right? X squared minus x is the expanded form. 2 proteins x plus 2, you just expand it. I thought we were close to calculus. Instead, I'm doing basic stuff like this that I forgot to do in the past. Forgot I didn't do this yet. I'm pretty sure we did simplified polynomials. Did we do simplified polynomials before I? Oh, no, we did not. Oh, I said I'm going to double check the star method too. Okay. Equal one. As you know, you can move a constant, move anything to make it into a zero on one side. And after that, you just need to find the factors. And then this, of course, is 2, 3, 1, 1. And you figure out over here that if, wait, this is wrong. It's minus over here, so minus. So one of them has to be a minus. In this case, is this. This one you actually do need to do a lot of practice. And Gita Swap really helped me on this one. This is not something you can get easily, um, in my opinion. So I believe this is multiplication this way, and when you do multiplication this way and that way, you have to add up, add them up, add this way up over here. Yeah. Actually, thinking about it, my way in Guitar Spark is harder. Maybe the star method is easier. Actually, I think I did cover this one. Um, but let me just do this real quick. That's how I did it. No. Funny part is I usually use my graphing calculator on this stuff. Um, But anyways, if you multiply this across, you're getting -2 and 3, which is not right. No, sorry, across, sorry. I did it wrong. So you just go over here, and that's 2, and you go over here, that's -3, and that is -1. There you go. And then the dotted lines are for, uh, I should, I should make this more obvious. Uh, Sometimes I do use the basic forms. Okay, so yeah, -1. And -1, if you know, this is the middle part, and that's how we know it's correct. Now, the star method is probably easier for most people, learning in the American education system. But in the end of the day, you get -1 and 3x plus 1, basically. And you get the right answer. I know that's correct because I've done this multiple times. So I do this one more time over here. Uh, do we do it multiple? We do the same fucking method multiple times. Okay. All right. Whatever. This one I think was to show that you can drag common units out, which gives you this equal 0. Uh, oh, I'm too lazy to actually type it out properly. I'm just gonna hope no one notices when I do this. Yeah, no one will notice that. I mean, I can make it more cleaner by alt, like that, and no one will notice that I did that to it. Hey. Anyways, then you get 2, 3, -1, 1, and you know that these across equals -3. Oh, this is the same thing, isn't it? -1, yeah. Anyways, it's 2, 3x plus 1, parentheses 2x minus 1, basically. Okay, a more interesting one is this one over here, where you get this stuff, because what you're trying to find out here is a perfect square over here. I should have explained this is a perfect square. Why I say this is that in my experience with some of my professors, they just love to make questions that give you a perfect square, and you kind of expect it to know it automatically. So I had it happen a few times, which honestly I should have expected. Now I realize a lot of times you get it into this form, and it might be more obvious that way. I don't know why I chose to Z. I don't know why, and I'm not going to change it. That'll be a pain of that, a pain. Another type you might see that's very common, because a lot of professors love it, because you don't need a calculator then. Well, at least that's my experience with some of the no calculator professors. Uh, had that for Math 20 something. Anyways, with this you can kind of get the idea that there is a square minus b. Oh, well, for some reason I chose to leave the b as just b. I don't know why. Equal a plus square root of b parentheses a minus square root of b. Um, it's the same thing as if you were saying a squared minus b squared, which that would also equal a plus b squared parentheses a minus b. You get the point. And then you get a simplified thing over here because of that relationship. Uh, do I need to do? Yes, I should do this one. Okay, let's do it. X4 plus 6x squared equals 0. Now let's, yes, what the, oh, okay. So this is true if you know what B is. B is the middle, but I never explained it ever. So how did I expect you to know? Oh, I can actually change this. Well, let me just put it this way, make it easier for you. Yes, let me clear this and make it easier. X squared plus bx plus b squared minus 2 minus b squared divided by 2, and this squares out equals 0 is true because this is a perfect square or something along the lines of a perfect. Yes, it is a perfect square. That's what it would work. Now, imagine if x4 is subbed by u, x prime or something like that. That's what's happening over here. So if x4 plus 6x squared equals 0, and you say x, what's happening here? Um, uh, what the hell happened? Okay, I don't know what happened. I'm just gonna redo it again. X4 plus 6x equals 0. Now let's put u equal x squared. That gives you this uh, 6u, and then that's why this works. You can treat it as like a normal polynomial expansion, and in all honesty, you don't have to do a u sub that case. That's why I just went over here like this. Even though it's a part of 4, the reason this works is because of the even numbers. Like there's only two of them, and it's all even, so you're fine. So yes, you go 4 plus 6x plus 9 minus 9 equals 0. Why you do that is because this is a perfect square, which means this is given into x squared plus 3 square. And you don't have to even do this stuff. I did it because to showcase it, but you should be able to instantly, I mean, you should know it already. And then from that knowledge, you still have that equal to minus 9, which equals positive 9. Um, you're going to have to do the plus and minus square root rule, which gives you x squared plus 3. And you can do the square root because this is just a number and this is a parenthesis, so you can just do that way. Um, now, this is equal. Now, because of that, you're going to have many solutions because first of all, plus minus square root of 3, sorry, that's already plus or minus 3, and then it's plus 3 again. Is it plus 3 or minus 3? Uh, it's minus 3, right? Minus 3, sorry. Just leave that in there. And let me just erase this and then change that to a minus. And it's x equal then square root of plus and minus 3, which is what we kind of got. There should be uh, 1, 2, 3. Why is there only 3 solutions? There should be 4. Why? Why is there only 3 solutions? There should be 4 solutions to this. What the fuck did I do wrong here? So let me see this. Square root of 3 minus 3 plus or minus, right? Plus or minus. So if it's minus square root of 3 minus 3 equals 0. Oh, because there's a negative version of it that will also give you 0, so you're fine. Okay. Yeah, I'm right. Not wrong. But I do not like how blurry this is. Can I make it less blurry by shortening it, maybe? I know. But at this point, you already know this from like multiple times of doing it. So yeah, that looks a little better. And let me just do ax square root 2 plus b. I think we uh maybe we do. Uh, did we do equation graphing yet? Oh yeah, you should already know this. Plus c equals 0 is a standard form. Yeah, you should already know what the standard form is. I thought you didn't know for some reason. Okay, more factoring. We don't need to do this. It's more like this. The reason I put a lot of factoring questions at the end is because it's like Gitansalov, and you just have to do multiple questions on this. And I don't know why, but they love to do it because no calculators, and they love to do this to you. Oh yeah, I do not want to do this part because it's painful. Just know that this is the solution and this is the easy way. And the hard way sucks. But it does give you a certain algebraic intuition in the end, which is why I'm gonna go through the process of it, but not really like I don't want to ever touch that ever again after I explain the process of it. Okay, the first way is if A equal X and B equal X, and you're gonna ask, oh, the first way is over here. You're gonna ask, why the hell am I doing this question? Um, yeah, why the hell did I make this question? I ask myself that sometimes, but it did have an interesting point. So if you realize that this is just x squared 15 plus x squared 15, then you realize that only zero x equals 0 works, okay? Now, imagine if you were to do this painful stuff where you claim that b equal x and y equal x. Um, and then, you know what? It's so stupid, but it has only one reason I want to keep it. It's just the idea that imaginary cannot cancel out with real. So over here, you see over here that imaginary, and even if you wanted to cancel out, what happens is that the imaginary and then real basically there's no way for you to get that cancellation going on. It's like your phased direction, the angle directions in two different directions. So no matter what, even if you say the only way for this to work is if x equal to 0, basically. Uh, Otherwise, there's no way the phase angle can make it happen. But I'm now realizing this is an awful question. I'm genuinely worried about my sanity on this one because it took forever on this one. um, but I still like the question. Why do I like a horrible way to do it? Um, no, 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 no. I'm just gonna. If there's no value to this question, I'm deleting it all. Though. Yes, there's no value to this question. It's for miserable amounts of pain, right? I mean, you could reframe that question. Yes, yes, yes. So instead of writing this, I can say claim b equal x. Um, I mean, I don't like it doing here. I'm gonna do it outside. There's a way to make this question actually palatable. I didn't think of this before, but it's actually palatable if I say something like this. Um, claim a equal a and b equal x. And then solve it. Yeah, yeah. Now it makes like it has something. But what the hell? There's a line over there? I did not, I genuinely forgot that I made a dumb barrier here. No, I made a dumb barrier over here, but I didn't make a dumb barrier. Awesome. What am I doing with my life? Just delete this then. Oh, if you're gonna make a barrier, make it a left and right, is what I say now. Um, Now, so because of that, I can now grab this one. Yeah, that was my latex. You'll see it later. I make latex and then screenshot it and put it in here. You'll see what I mean. Now, with that said, how much of this can I delete after that? Um, all of this, right? Because this is awful. This question is garbage. I mean, yeah, there's no point in it. I mean, that has a point. This can have a point, but the other way of doing it had literally no point. Insert table two, and then there you go. There's one, there's two, and then we'll just put this in the middle, and then we'll just do this, and then we'll just do highlight and table properties. I'm not gonna worry about that, and then change this middle one, middle property, to black. And then we'll just delete this section entirely. And then we'll move this up. Yeah, there you go. Beautiful. Um, yeah, it has it gives you something at least. Uh, yeah, and I know that's correct because I have done that multiple times just to make sure that's correct. Um, it's basically more of the same. This is more valuable because it's just immensely more valuable than earlier. That was such an awful question, man. Okay. But honestly, it's just solving a squared plus ax plus x squared equals 0, basically. uh, but uh, it's easier to look at it as x squared plus ax uh, equal minus a squared. I should have changed it, but it doesn't matter. Fine. And then you can realize that through the b square 4 process, this is a squared divided by 4, which then you can bring back. No, you should not bring. And then you have to do a squared minus 4 equal minus a squared. Realizing that uh, this is a perfect square and this can move to the other side, you get this function and you keep on going like that. Uh, very simple. Honestly, I wouldn't go. I'm thinking, will I use that? No, I would use it to PR quadratic form, But yeah, after you get x squared plus ax plus a squared divided by 4 equal negative 3a squared divided by 4, all that's left is just say this. And then you square root this, plus or minus, and then say x equal plus or minus square root of 3 negative a squared 4 minus a divided by square. And the reason I did the last step is some annoying person will say, that's not correct. You have to go and do the final step to do this plus or minus a divided by 2, even though it doesn't matter. Now, if I was to actually graph this, what would it look like? It would look like a vector, and I'm not going to actually do it because it's not the scope of this section, but I should not do this, but let's just say this is A. For some reason, the circle is A. Now we have a divided by 2, so it's negative, so we go over here. So we round vector over here, and then it's plus or minus, so it's going to look something like this, square root of 3, which is smaller than 1, so it's going to be looking like this. Is smaller than 1? I don't know, but it looks like this. All right. And this can be important when we do gain value analysis in control theory, if I ever get to it, which will probably take 10 years at this point because the rate I'm going at a slug's pace. This is gonna take 5 years. At the rate I'm going, that's for sure. I'm going at a slug pace. At least I'm fixing up everything. Anyways, next up, more expanding, I think. Earlier I explained enough of. Actually, I did this already, didn't I? Oh, we did. Yeah, we don't need to go back to that. Oh, proving this. Oh God, this is a pain in the ass. This proof is like, just pain because what? I mean, there's I guess some need for it, but so first you divide by a on everything, and to add both sides, you're gonna do a perfect square shenanigans again, because it's perfect square shenanigans again. Basically is what's happening. If you remember how to do perfect squares, it's basically doing that, just making it more easy for anyone to get that formula. Uh, basically, does that make sense? Yes, I think it says. It's not hard, honestly. It's just getting the perfect square formula and making it like universally possible to read. So this is a perfect square now, which I already say second perfect square over here, which is why this is x plus b divided by 2a square, which equals negative c divided by a plus this equation here. Now you can just do more algebra until you get this form. Now this form over here, you're just gonna memorize it. Just grab your calculator always. If you're allowed, you should, interesting. And the professor, some professors love to do this because for some reason, if they allow the scientific graphing calculator, there's no way to solve this question. I mean, it's easy to solve with a graphing calculator, but if you're given a fucking scientific graph calculator, there's always like a second poly sometimes, and it gets really annoying in math classes. At least the math class I have to do. Anyways, this is just plug and chug at this point with a calculator until we get this proof, which we have done, right? I have done this before. It was a pain, but we did it. Also, we did do that. Okay, I'm a fool. Over here. Okay. Okay. All right. Exponent. Did I explain E equals 2.17? Yeah. E equal 2.17. Something, something, something. Euler's number. Okay. Euler's number is special because of the property of it having a lot of weird limits go to it, first of all. And you can show this off, which shows that every single cosine and sine is actually an imaginary thing, has imaginary numbers in it. And with Euler's equation, you can see also Euler allows us to basically it is a derivative of a derivative. So if you have a periodic thing that's always periodic, well, it's possible to show it with Euler usually because of the property of the derivative of e to the x is equal to e to the x. What that allows us to kind of give an intuitive reason why this works is because if something is periodic, and it just shifts the plane a little bit when you take the derivative of it. Wouldn't it make sense if Euler, because of the proper derivative, to if you get it in the right form, you're allowed to get that periodic function multiple times. If you do it multiple times, if you because sine and cosine, if you do enough derivatives, it eventually loops back to cosine again. So what does that really mean? It just is an intuitive reasoning why this is true. Yeah. Yeah. I just yeah. Uh, there you go. So Euler's number. Although in this case you probably don't know much about what Euler is. Now you add it all up over here. This is basically saying if you have A times A times A times A, you get AN. We're just using the plural down over here this time. And then if you're multiplying this and then multiplying again with here, you're basically getting a bigger addition, additioning the exponents. That's why you can just do this. Yeah. And now the down below is more confusing, but basically you have multiple of this, and you can see this as A uh, uh, N, which is going to be AN over here, and then M. So basically AN 1, AN 2, AN 3. Basically, it's what's happening, which shows that why you can multiply if you have parentheses, and then so on, so on. Uh, and then basically we do just simplifying some exponents because we can. Uh, and then we go into a little bit of this, which um, system. So we can do 2x plus y and x minus 2y equal 1. You can have either one solution, infinite solution, or no solution. Because we're dealing with 2D at this point in time. Basically, it's a 2D world, which means if you have two lines somewhere, because these are lines in the end of the day, there's only a few ways to get it. You can have a line on a line, or parallel lines, or that has no solution, or a crossing line that has one solution. And remember, these are crossing lines, so that's the only way that can in 2D. So that's the only way that can happen. So yeah, and you'd be shocked and surprised how many of these real life functions can act like this. Some of them, this looks professional enough, so I kept it in like that. And then we go into some Cartesian plane shenanigans. You can have fun with them. I remember checking all of these a long time ago. There's no mistake. They're just a pain in the ass a little bit. Um, now the one thing I have to show you is here. Is what does this absolute value mean? So we're getting rid of direction, but EI theta works. Do you get why it works? Because EI theta is equal to cosine theta plus I sine theta. So when you get the absolute value of it, you're just streaking it. So that's why what you're doing is inputting a direction into an indirectional magnitude, and that's why it works. And then you just get rid of the imaginary and figure out when that imaginary turns zero, which is in this case, which makes you get 3 divided by 2, right, plus or minus, and then kind of like that. But you could do all that fancy stuff. Oh, let's see, this is a little confusing. But all I want to say is all you have to say is only when theta real. Well, maybe say x equals real. So all the imaginary goes away, and there's a valid answer. And you just have to leave it like that. And then more solutions like that. Oh no, we didn't do basic. There's some more graphing things you can do. Yeah, sure. Okay. Anyways, there's no, and then the log, same reasoning as last time, minus minus, you know, Fibonacci numbers with expansion, and then some fraction decomposition. I think we're good. I think we're you can read on your own time. Actually, I'll explain when I'm not tired. It's like 2 o'clock p.m. a.m. I need to sleep. Um, so we start here with an array, which is a vector basically, and then a segment, and then a line. The difference is that this is one directional to infinity. Actually, maybe it's not a vector, it's more of an array, but it works as that. And then segment has finite, while a line goes forever. This is the right triangle, and then we get a triangle like this, and then we get a reflection over here. This is definition, so it makes sense. And then the angles, and then we get the angle. I love this one because you're making meters divided by meters. What this gives you is radians. And radians is actually a dimensionless parameter. And as a lot of people say, physics doesn't care about dimensions ever. And I actually agree with you. Um, so there you go. One of the many dimensions variable. The first one you ever learn, radians. Now degree actually adds a human unit to it, which is this. So it doesn't count as dimensionless because you're forcing it to measure in a different way than getting a dimensionless answer. So always make sure it's dimensionless is what we say. Degrees is not dimensionless because you're adding some human element to it to make it measure something in a 360 something. Right? That's what I was told. Anyways, here's more conversion things, and here's a acute obtuse right angle, which is basically just less than 90. So 90 is over here, so less than, greater than. And then equilateral locus scaling, we all know those. You can read them, they're just definitions. And we do a one question. Basically, this angle should equal this angle, and then this angle should equal 180 because of the rule we made up over here. And we talked about supplementary angles being 180 and then 90 complementary. So and then that's just algebra to get the right answer, and that's just algebra. Radians is very less intuitive. That's why we use degrees, but there's some value to radians. All right. And then, oh, here's an interesting one. So here is getting the triangle to A to B. We move here to over here. The way I did it, there's many solutions, but the way I did it is move over here, reflect it across the x equal 2, and then dial it back in the y directions like that. This one I did, I believe is this line over here. Reflect at that point, right? And then that would have gotten this. Notice that the scale is divided by 2 over here, so you just dial in by 2 at point 1 and the negative. Did I do this wrong? 1 negative 1. Yes, I did this. Probably drunk, sleeping. Anyways, over here we show the bisector, what a trisector is, the convex paragraph, and the concave polygon is, and then concave is uh, over 180 uh, is concave. Uh, any one angle over 180 is concave. And then we're done for now because I'm sleepy. But we could next one is all right. Oh, this weird ass proof. I should probably delete it. Yeah. Well. I'm not gonna talk about it. It's a weird ass proof, honestly. Um, yeah, okay, yeah. Next is just gonna be a lot weirder. Okay, I'm gonna stop here.